Okay, welcome everyone. It's very exciting to have a huge participation interest in our fourth workshop that we are hosting through SkillSurf, which is the System on a Chip or SoC Design Workshop. This is the first time we're doing a 4-day free workshop series, and we have a few interesting workshops planned in the future as well, which I'll be going through. Okay. So just taking 5 minutes here to cover a brief history of SkillSurf and what exactly that it is we are trying to do with our efforts through these workshops and courses that some of you may have already been a part of. Um, so this is a kind of an old slide actually. Uh, Back in March 2021, uh, during like the COVID-19 years, me and Abba had this idea about introducing the missing semester concept, which is how do we develop skills in the Sri Lankan undergraduate community that sort of universities um, um, don't have the capacity or the sort of opportunity to develop in students. And this idea sort of evolved into what SkillSurf is today. Back then, we focused mainly on embedded systems for beginners, and we did sort of like free workshops, small workshops over the weekend, starting with this first one in May 2021. And back then, me, Dr. Subodha, Abba, and few of our final undergraduates helped deliver the first workshop. And um, we sort of formed SkillSurf as a non-profit organization out of the Department of Electronics and Telecommunication Engineering from the University of Mortua, focusing on key areas that needed to be developed in Sri Lanka's technological ecosystem. Sort of like to bring all these like high tech areas that sort of have built the best industries around the world, bring that knowledge and that technical expertise to the Sri Lankan ecosystem. And yeah, that was kind of our mission. And we have so far done like a few different programs under like this four areas of SkillSurf. Workshops wise, I'll focus on like skill casts today. Um, so yeah, mainly we've in the past we've done embedded systems, generative AI, quantum computing, and last year we did analog IC design, which was also pretty successful. So yeah, this one we started with uh, the quantum computing workshop. Interestingly, we invited Dr. Harini um, uh, in 2023 to conduct the keynote speech. Today, Dr. Harini's husband, Dr. Dinuka, is here today to do the keynote speech. Pretty cool. And then 2024, we did generative AI with Dr. Sadeep as the keynote speaker. And then last year, we did the art of analog IC design with Dr. Nilan as the keynote speaker. And this year, we are, as you know, doing system on a chip. And I hope all of you really um, find this an exciting workshop and get the maximum use out of it. Um, yeah, and also we have some future workshops planned. We're currently looking into developing a workshop around digital IC design, and also we have started preparing some material to deliver the RFIC design workshop, which I think might get delayed to next year. Um, okay, I think with that, um, I won't take too much more time. So I think with that, we can move on to the main part of the workshop. So Abba, if you're ready, yeah, we can get
Yeah,
started.
all right. So let me share my screen. All right. Hello everyone. Can you hear me?
Yeah, we can hear
Am
you.
I audible? Okay, great. Excellent. All right. So I'm Abba. I'm a PhD student in UCSD, and I've done my internship in Qualcomm and AMD, and so I have some experience in like working at a chip design startup, and so I did my undergrad in ENTC, Sri Lanka. So this is my website, and yeah, so and you can check some of the SoC projects I have. So and like if you want to see like some example projects and stuff, you can check it out here. So I can share the link over here as well. Right. So right, great. So basically, like yeah, and you can see a few projects over here. So like I'll briefly talk about some of them at the very end. So this is a like a small neural network accelerator with Python front end and tickle scripts for building it in say FPGA and for like ASIC and like in different ways. And so there are some formal VIPs and we also have building some fuzzing frameworks. And this is the main project that I'll be talking about today, the systolic array. So, and yeah, so this is mainly like to be used as educational or to be used as a test bed. So basically, yeah, so this is what like we will be covering at the end. So the repo for this one is over here, and we'll be sharing this as well. So yeah, all right, excellent. And yeah, so yeah, speaking about the open source tools, so like and these days I'm using that to build some of the very beginner content as well. So like you have stuff like this. So this is a page for a course that we are building and at UCSD. And you can see like some of the end-to-end like system designs for without like what advanced protocols like XE that we are going to teach in this course. So this one will be like much simpler. But here we have some of the modules, and then you can also see like how things get taped out, as well as like the standard cells. So stuff like that as well. So and all this using open source tools, and that can be reproduced. So if you're interested in this sort of thing, you can check this out. And this is like a FAR filter on using UART on an FPGA, which you can put, as well as this on GDS. Yeah. So yeah, these are some of the stuff that we are doing. And to go into today's workshop, um, yes. So just like we saw in the previous session, which was very informative, the modern SoCs are like pretty complex, and you have like so these are the what like the Apple chips M3 and A19, and you have like all these different like picos and the efficiency goes, and then you have like memory. So you have like a ton of things that are working together, like a lot of those in the same die, and now you have like multiple dies as well. So the SoCs are becoming more and more complex, and it is becoming a very like interesting field, right? So the sort of like when you talk about in the SoC level design, so what we generally talk about is like the protocols and how things generally talk with each other, and like how do you solve this, like say timing problems and all of that, right? So this workshop will be sort of like an introduction on that. And what the final project or like the sort of like thing that I'll be walking through is like um, an XE stream systolic array, and like we'll be using some XE like modules, open source XE modules, to put it together and connect it with IBEX SoC. So this IBEX is a RISC-V CPU. So you can write your C code and you can run it in the IBEX CPU. So it has been taped out a couple of times, And but in this course, we'll be doing it through simulation. So you can basically simulate, you can write a C code, and you can let the CPU run the C code in simulation, in a clock cycle accurate simulation, right, through Verilator. So that's what we'll be doing. And this CPU will be controlling and talking to our own design, right, which is the systolic array. And yeah, so this is the systolic array, and it's an access stream systolic array. So which means the like a systolic array basically does the matrix multiplication, right? So it takes two matrices and you multiply and you give the output matrix. So like many of the popular like neural network accelerators are systolic arrays. So Google's TPU like is a massive, like started as a big systolic array, and I think the Amazon one, Microsoft one, like they are also what based on systolic arrays. So it's like what it's a very old, like it's from 1980s, the basic architecture, and it's still very relevant, and it's used a lot. So the data will be going through access stream ports. So what is access stream? We'll be looking at it in a second. But yeah, so the data will be, I'm giving like an overall picture here. So you will get an understanding of what we will be doing and like through the this workshop. Okay. And if you sort of know all this stuff, then like, I mean, what you probably know everything, right? So yeah, so that way, like you can like, I mean, figure out whether the workshop will be useful for you or not as well. All right. So you will have the data will be coming through two matrices, will be coming through these access stream ports on these two sides, and they'll get multiplied, and the result will go through the another access stream port, so like the matrix, right? And here we'll have a simple sort of like a synchronizer to synchronize these two ports, and then the output matrix we will add with a partial sum matrix, right? So this is like a classic operation you do, like if you are doing tiled matrix multiplication, right? So we'll multiply this thing, and we'll add the partial sum with the resulting matrix, and the result will basically put it out. So if you look at this in the top right corner, so this is the operation like we will be doing. So let me read them right. Yeah, this operation we'll be doing. Okay, so that is k is the like a so like one matrix. So, and we multiply k with x, we add with a, and that's the output matrix y. And then, so this R is the number of rows and C is the number of columns in the systolic array, right? And yeah, so, all right. Okay, so we'll have a synchronizer here as well. And these are like DMAs. So the soft DMAs, they basically like a bridge between the full XC port and an access stream ports. So what are these ports? Like we will talk about it throughout this course, and I will introduce like these protocols and like all of those. So, and then we'll gradually build towards like the entire system, right? And these are adapters. So they basically convert the sizes from like, for example, like this is 128 bits. And if you want something like 100 bits or something, then you can use the adapter to convert from 128 to 100 bits, right? So they do that. And we'll also talk about how to do software map registers. So that means like you have a register file over here, and this register file can be written from the CPU, right? So this is your own register bank where you can write into and read from to see the status of your accelerator, right? You can do all those things, and that is done through an XC Lite port, right? And so we will write this part as well, and then like all of this put together will be the top XC module. And we also have this XC interconnect, like I mean, into this. So all of these are open source modules. So like how do we, like I mean, we'll be looking into how we put all of this together. So this is an open source module, and this DMAs are open source, and this XC adapter is streaming adapter is open source. So only this orange stuff and like only these things like I have written like by hand in Verilog. But other than this, like everything else, and this one also I have written. And the other stuff are basically what open source modules that I put together. So this is something that will like that is extremely powerful. And if you are a university student or something, then I think this is extremely valuable for you, because I think that like writing some module like this by itself is like and testing it very well and like anything useful or novel. So that is like pretty hard, right? And once you do all of that, then if you want to see it working somewhere, then you need to actually do all of the other things, right? So all of these other things. So and writing all of this by hand is like near impossible. So that will take like another year or something if you want to build everything by hand. So, and that is not necessary also, right? Why all these modules are available as open source, and you only have to put it together, and you need to know how to put it together and how to work with them, right? So once you do that, like you can basically like take whatever module you write, and you can make it into a full SoC. You can put it on FPGAs, and you can test it with what these soft processors, and you can even generate like a GDS and like basically measure how much area or violations or everything, right? So you can do all of that. All right. So to connect this module, so this is sort of my top module. This top taxi int is my top module. But then, and I have put this in FPGAs. And then like to connect this to IBEX REST file. So IBEX doesn't support XC by itself. So it has its own protocol. So to convert this to own protocol, like we need these converters. And then using these converters, we put like this system historic array for IBEX. And then we have the IBEX bus and timer and simulated trace and memory. All these are coming from the IBEX example, right? And that is how basically the whole thing is like put together, right? So yeah, main and firmware and system. All right. So yeah, do you have any questions? Okay. So there's a question, isn't DMA controller available as an IP in Vivado? So I'm not using Xilinx IPs. So like a few years ago, I was using Xilinx IPs, but then I found they are like a bit of a pain to work with, and also they are not very performant. So and yeah, so and they take like too much area as well. So I found like it's actually better to use open source tools, open source IPs, and instantiate them in Verilog directly, right? So that way, you can actually get much better performance. Like I'll talk about it when we talk about DMA control. Okay, so yeah, that's what we'll be doing. So what you can do if you want to replicate this whole thing, okay? So before we go any deeper, what you can do is basically, um, yeah. So go to this website, this repo, and I have shared it in the chat, I guess. Yes, yeah. Okay. So you go there and mm, right. Okay. So clone this repo, and from inside, what you do is basically do a make fresh. Okay. So I have the instructions down here. Okay. So I have the instructions written here. So if you do make fresh, it will create a Docker container, right? It will create a Docker container for you. And then what you do is you do make enter. And if you enter, like you are inside the container, okay. And from the inside the container, you can do make query, and this what it will run the validate simulation, right? So for the whole thing, and then you can open your files and everything, and you can see like how things are connected and everything you want. Okay, so yeah, all right, and yeah, so this basically test the C firmware and the SoC and everything together in like one place. Okay, so we'll be basically walking through that in this workshop. All right. So before we move on, do you have any questions so far? All right. So okay. So before we just jump into systolic array, we will discuss something about like maybe we'll take like a smaller design and okay. Can you specify the command again? All right. So it is mentioned in the repo as well. So it's basically like so you just go in there and do like make fresh to create the repo. Okay. and then you do make enter, and from inside you do make query. Okay, so it is I have written that in the red here as well. So here you do make fresh and make enter, and from inside you can do make query. So yeah, so these things are optional. You can just do make query to run that later on. Okay, all right. So okay, so let's do okay. So before we go into the actual historic array, let's look at a much simpler design. So that way we can focus on the actual SoC without getting down into the problems of what I mean, like the data flow in systolic array and everything, right? So this will be like a much simpler axis stream vector multiply add, right? So yeah, so we'll first start with the vector multiply add, and then we'll see how we can convert that into axis stream. Okay, all right. So a vector multiply add is basically like this. So the idea is like we want to element wise multiply and add vectors, right? So let's say we have two vectors, the three vectors. So k, x, and a, right? So we want to multiply the 0 and 0, multiply this together and add with a0, and that will be the output, y0, right? So similarly, k1, x1, a1, it's a y1. So this way, like we want to do it in parallel for a very large number of values, right? So we can do this. So, right. So this is the vector map that we'll be looking at. So, and we'll be doing like out of all this, we'll be doing like R of these elements in parallel, right? So what does that mean? So that means like, I mean, let's say you have 1,000 numbers like this and you want to add like 1,000 numbers. So like, yeah. So we'll do like probably maybe four of them at once. Okay. So these four of them we'll do at once. So four of them will come in parallel and you multiply and add, and you get an output. So this one, yeah. So that's the idea. So, okay. And the output is also registered. So you have a latency of 1, right? So this is like the basic Verilog code to do this. Okay. So let me walk you through that. Okay. So basically we have the R. So like number of rows in this. So how many rows? So let's say 4. Okay. And this is the width of K is 8 bits. Width of X is 8 bits. Width of A is the like of this one partial sum, that is 32 bits. Let's say the width of W is also 32 bits, right? So W is the output. Sorry, the Y is the output. That's also 32 bit, right? So, and then we have our reset and enable, like, yeah. And now these are coming as buses. So, which means like we are getting each element is WK wide. Okay. And like that, you have R elements. So this is a packed array in system Verilog, right? So, yeah. And the reason I'm using the packed array is because it's easy to index. So I can just, I mean, access this data like this. Otherwise, you know, like you have to do some, like, I mean, you have to do some arithmetic to capture the data. And that is like pretty error prone, right? So you can just get the data like that, get the element like that. So similarly, you have X data, which is X size and A size and Y size, right? Okay. So now you go through this. So now you have a for loop, and this for loop is like 1 per element, right? So how many elements are there? R elements. So for every R, you are doing a for loop, right? So if R is 3 or something, then we'll do for 3. Okay. And yeah. So, and if it is reset, we'll write 0 if it is, and if it is enabled. So like we have a clock enable port, and when enable is high, we will update this with a value, right? So what is the value? So the value is basically like we do a signed operation here. So signed K into X plus A, right? So, and we do that for every single R from 0 to R minus 1, right? And so which means like this is a generate for loop. So we get the R elements in parallel, right? So, and this synthesizable code, right? So you get R elements in parallel, and each element is doing this separate this operation. Okay. So yeah. So this circuit, the Verilog code, system Verilog code here is the description of this circuit, right? So does any of you have any questions in this before we move? All right. So if there are no questions, yeah, we can move from here. So clear. Okay. So now let's talk about stream data. Okay. So like we are going to like talk about axis stream. So before that, like what is stream data? So the idea of streaming is basically like, I mean, let's say some like one example. So you want to process a video, say through a neural network, right? So you want to transform, you want to do some transformations on top of each other. So you want to take like a video and you want to do like apply it through like every frame through a neural network or something, right? So you may want to say detect vehicles, so you may want to sort of like do something to the video, right? So how do you do this? So what you can do is basically something like yeah. So you have like a video decoding here. Okay. So like, I mean, you can have multiple modules. So you have a video decoding module and you get the data, let's say 128 bits, and then you like multiply and do something. And the result of that, you put it in layer one, result of that layer two, result of the layer three, right? So, right. So now you have like, I mean, like a very basic case over here would be something like, let's say, like, I mean, you're actually processing everything. So you're doing all your video decoding in one clock cycle, right? So you're getting all the data and you're doing video recording in one clock cycle. And you are doing all your layer one in one clock cycle, and layer two in one clock cycle, and layer three in one clock cycle. So this is sort of the best case scenario, right? So if you get like maximum performance, this is what you do, right? But this is not like very realistic. Okay. So we will relax these assumptions one by one. Okay. So then, like, I mean, okay, so we name this ports as master or manager. So that is where, like, if you are the guy who is giving data, then you are the master or manager. And if this port is receiving data, so it's a slave or a subordinate, right? So it's a data output and an input. So we call it like the manager and subordinate, right? M and S. Okay. So now let's look into our let's relax these conditions. So if you can see that in the real world, okay, so you can't actually do the entire video decoding in one clock cycle. You need multiple clock cycles to do stuff. So this means you can't actually output the data in every clock, right? So sometimes, like in most of the cases, so you need multiple clocks to process, and when the data is ready, you need to output, right? So similarly, you can't also take new data in every clock cycle, right? So if you can take data every clock and if you can give it every clock, then this whole thing becomes a simple pipeline, right? So each of this will have one register each, and your data will go in like that, like you just keep pushing data at a maximum throughput. But because you can't take data in every clock cycle and you can't give out data in every clock cycle, you need like a bus protocol, right? You need handshake mechanism. So that is where access stream comes in, right? Okay. So there are some additional constraints. So that is that the packet size. So in this, like in the simple in a general case, so a packet size. So what is a packet? Packet means like a video, like say a frame. Okay. So this video frame size should be a multiple of the bus width in the here, right? So here this 128 bits. So your video should be multiple of 128 but 32, no 16 something. So yeah, 16. So it should be a multiple of 16 bytes. Okay, your video frame. If it is more than 16 bytes, maybe 17 or 18 bytes, then you have a problem, right? Why? Maybe the last beat will have some invalid data if you if it is not a multiple of 16, right? So you have that problem. So you have to solve that also, right? And then you have like, okay. And the other thing is like every module also needs to know the size of the input packet. So how many bits, right? So you need to know this packet is what is the size of the packet. So let's say if it is like 1024 or something, then 1024 divided by 128, and that many beats, that many clock cycles is one packet. You need to know that. So and then you have to keep a counter here, and you have to keep counting that. So these are all problems if you simply implement this design as this like one cycle or like very simple module, right? So to solve each of these problems, we are going to introduce a bunch of new features, and that features will be the access stream protocol, right? So let's see how that goes. So yeah, so this is the like, okay, so the simplest one. So you have let's say one layer, and now you have S and M, right? So the input and output data, and you have a like clock and reset time, right? Right. So you can't output data in every clock cycle, right? So you need more time to process data. So then what do? You have this valid signal. So whenever this valid is high, then only the data is valid, right? So that's why you have the valid signal. And this can be zero most of the time. And whenever you have data, it can be high, right? So otherwise, you don't have to worry about the data at all. Okay. So, and the other issue is you can't take in data every clock cycle, right? So why? Because you might be busy. So you might need more time to process the current data. So you can't take new data every clock cycle. So for this, you have the ready signal, right? So, and when you are ready, you can accept the data. Otherwise, like, whoever is giving you the data, the manager has to wait, right? So, and the third one is a problem that is like your packet size must be a multiple of 32 or like 16 or something, right? So how do you solve that? To solve that, you have this keep. Okay. So here it's a 32 bits. So the packet size must be a multiple of 32. To avoid that, what you can have is you have this keep signal. So now your packet size can be anything, right? So it can be 33, like, not exactly 30, 33, but like, say 36 bits or something, right? So then, like, what you have is basically this on the last beat, last clock cycle, the stick keep will be high only for the like valid ones. It will be not valid for anything else, right? So, and from this, you know whether these four like lanes or these 4 bytes inside this data, they are valid or not, right? So, yeah, so that helps with that. So now you can actually send data that is more than, or like, it is not a multiple of the S data number of bytes. Okay. So the next one is like you need to know the packet size, and you need to have to keep a counter. So you don't know how many clock cycles it takes to send a packet, right? So you have to keep a counter and all. So to avoid this, you can have a last, right? So you have an S last and you have an M last. So this will go high in the last clock cycle of a transfer, right? So if you're sending like one big packet, and at the very end, very last clock cycle of the packet, this T last will go high, and that is how your following module knows that okay, now you are done with the data, right? So and this is very helpful for that. And then if you want to send anything extra, any other information, you can send it through T user. Okay, so this is you can set whatever size you want, and you can send data you. All right. So there are some other signals called ID, strobe, and destination, but they are like not very important or not super useful for our use case. So yeah. All right. So you have any questions with this? You can ask me. Yeah, so by adding a TKPO, we can only have a packet size to be a multiple of 8 bits. This is true. Yes, it is true. So in the XC stream protocol, so XC is basically like the probably the most popular SoC protocol. So it is used in all your phones and all your like say Apple laptops and like over a ton of devices, right? On FPGAs and everything. So what the XC protocol is the one like that is used to communicate between say like different say CPU and GPU or like CPU and cache and like a lot of things in like many ARM most of the ARM cores and everything, right? So and in that like basically they have like I mean an XC protocol XC bus is made out of multiple XC stream bus. So like I mean it have 5 XC stream buses and this is one XC stream bus. So the protocol basically defines all these things. So it tells you like what like what is allowed and what is not allowed. So and this is like one of those things that like it is set in the protocol. That is the like you can't have anything like there is other than 8 bits. So you can't have 9 bits. So like it has to be a like multiple of 8 bits. So I think that is a like pretty like a valid one. And so I think like I mean, if you are making something like that works with your own design, you can have do whatever you want. But then if you are trying to use open source design, so if you are trying to use some other people's designs, then you have to stick to that. Yeah. Isn't there any concept of address in access string? Okay, that's a great question. No, because it's a streaming protocol. So streaming protocol means you are sending some packet to someone else. So and that someone else will take the packet and do some transformation. Or like I mean, just like the example I showed you before, right? So you get a video stream, and you basically you get a video frame as a packet, and that frame you do decoding, right? So you do decoding, and now it's you get a different packet, and that packet you give to some other IP, and this other IP will take that and apply the first layer of the neural network, and it will give the result as a packet, and that packet will go into another one, and you do like a second layer and third layer and so on and so on. So to do this, you don't need a address, right? So this is a streaming protocol, and the whole point of streaming protocol is to have a pipeline like this, right? So there are like many cases where you need a pipeline like this, right? Or you need to build a pipeline like this, and that is the best part of it. Like for an example, if you're building a systolic array, you don't need addressing, right? The systolic array doesn't have to care about fetching data from something. So the fetching data, that is a job of a DMA. So and DMA is an open source module. You can just put it and put everything together, right? So if you are writing a systolic array, you don't have to worry about writing the addressing part, right? Because that is very complicated, right? So you only have to worry about making the best systolic array out there. And then if you have your best systolic array, you can put a DMA, and the DMA will take care of the addressing, right? So this is what makes everything modular, so very easy to build. And like I mean, once you if you understand all this very well, then like what the designs you make, you can easily put it on FPGAs. You can easily put it on like what full chips, and then you can that way you can actually get like a lot of use out of it, right, without spending effort. All right, any other questions? All right, so yeah, let's move on to the next one. Okay, so now let's talk about some specifics in the access stream protocol. Okay, so here's a spec. You can go to the spec and look at their stuff. Okay, let me click that and see. Yep. So AMBA4 access stream protocol, and here like they have what defined all these very particular stuff. What are the signals and like what you should do and etc. etc. Right. So this is very useful, and if you are trying to understand something or something, and I think this is very simple. Yeah, it's like 40 pages only, and most of the pages are empty. So yeah, right. So then basically your protocol is this. That is okay. So now these are some specifics to the protocol that you have to be careful, like when building stuff for existing. So Yeah. So this is what I always recommend. Like if you are building some neural network accelerator, or if you are building a systolic array, or if you are building a fast Fourier transform, or like signal processing design, any other signal processing design, or if you are doing anything that does anything to data, make it access stream, right? Because access stream is a very simple protocol, and like if you follow the protocol very carefully, then you can basically, I mean, it's not hard to follow carefully. It's very simple, and then you can basically put it with other IPs and make it an SoC, right? Because like you have a lot of IPs online for existing, right? So is there any response or acknowledgement in access to me? Okay, that is a very good question. So the acknowledgement, okay, there's no acknowledgement because you are sending off a packet, and whoever is downstream, you assume they get the packet, right? So there is no like acknowledgement in access to me, right? Because it's a very simple protocol. It's used to just for data transformations, right? Okay, so that's what makes it beautiful. So you don't have to worry about like say acknowledgement, handling acknowledgement or anything if you're building an access point design. So you only have to worry about making it very performant. Okay, all right. So yeah, so the first one is basically okay. I thought ready signal is a kind of an XC. No. So a ready signal is basically says that the following module is ready to take the data. Okay. So, but then you sort of assume that like, I mean, if the valid and ready are both high, then the data has been accepted, right? So, yeah. So it is not exactly acknowledgement. Okay, it's a form of back pressure. So it's basically to prevent you from pushing data when the following module is not ready, right? When the following module is working on something, you don't want to push data, and like that way you will lose data. So to prevent that from happening, you have a back pressure where your subordinate can tell you that like, I mean, don't send me data. That is ready. Okay. All right. So okay. So like basically, okay. But in XC you have acknowledgement. So we'll look at that later. Okay. So in full XC you have like acknowledgement packets coming, and we'll look at that. All right. So the first part of the protocol is basically when you have not M ready. Okay. So that is when M ready is down. Okay. You are supposed to hold the invalid and M data and all of the signals, all other signals unchanged. Okay. So now this is pretty important. So like in the sense yeah. So whenever this M ready is down, you have to sort of keep everything unchanged. Okay. So why is it? Why is this? So the reason for this is basically now this gives you this like okay, like if you look at the other way around, when when you so this is your module, when you pull the SRD down, okay, whoever is giving you data, your manager will hold everything constant, right, without changing. So that means if you want more time to process something, okay, if you want say multiple clock cycles to process one data, you don't need to register the input, right? So the input, you don't have to copy it into a register. So that's what we usually do, right? Like, I mean, because, I mean, you might be worried that like the input might go away, right? But because of the access stream protocol, you don't have to worry about that, right? So you can, the input will stay stable as long as you keep the steady down. So that way you can take many cycles to process the data that is staying in the wire as it is. Okay. And once you are done, like you basically, once you finish and send the data, you raise S ready, and that way you can basically get the new data. Okay. So that's the first one. So, and the second one is basically when valid and ready, the transfer happens. Okay. So transfer means one beat. Okay. So when both valid and ready are high, then the transfer happens. So that is how the your subordinate knows that the transfer has happened. Okay. And that's how you also know the transfer has happened. So from your side, you can observe the ready, and the subordinate observes the valid, and both of that are high. Then you know like the data is gone. and you have to pull valid down if you don't have data to send, or else the subordinate has to pull ready down if they can't accept the data, right? So you have to do that. Okay. So, and because of this, now this is like 100% performant. So this is something you see in like some older buses. So they are not very like 100% performant. So because sometimes you have to send the data, and like in next clock cycle you send an acknowledgement, and after seeing the acknowledgement only you have to send the next data, right? So that will waste clock cycles. But in X stream there is no, like, I mean, you don't have to wait for anything. You in this clock cycle you know whether the data is accepted or not. So you can immediately put the next data in the bus. You can put the data like that. So that way, like every beat, you can have a new data if you want. So that way, like you get 100% performance, right? So it's a simple but very performant bus. Okay, so that's why you can transfer the data in every clock cycle, and that is like you get the 100% throughput of your like bus width, right? Yeah. So this is like a simple and extremely powerful. And now people are like, I mean, it's ARM, and they like, I mean, there are other buses which use the same ready valid handshake, right? So you have what I think the Link, they also use something like this. And then like, I mean, within companies, they have their own custom buses, but they are like still like ready and valid. Okay. So this is sort of like an example on this one. So like bus size is 4 bytes. Okay. And your packet size is 14 bytes. Okay. So, and number of transfers. So how many transfers do you have to do, okay, to send this data? So that is like if you like your bus is 14.4, and the way you do that is you do a sealing, right? Seal of 14 by 4. So 14 by 4 is what 3 point something, and then like sealing of that is 4, right? So that way you have 4, like basically you do like 4 transfers, 4 beats, right? So these are the D0, D1, D2, and D3, 4 beats, right? And here you can see clear all. Yeah. And you can see, okay, so in the cycle, the 4th clock cycle, okay, so you do 4 of these, and you can see the T keep, right? So the T keep signal, you see it's always 1 here, 1, 1, 1, 1, 1, 1, 1. So which means all of these like actual data, so you have to keep them. Okay, that's T keep. And in here, you know that the 0th and 1st data are valid. Okay, but the 2nd and 3rd data are not valid. Okay, so that is how you get like 14 total 14 bytes, right? So 12 and 2, you get 14. So yeah, and that is how you're able to send like over the like multiple of the bus width. Okay, so T keep works. And yeah, the next one is basically you have back pressure, right? So you get the back pressure from the slave or subordinate at cycles 4. So over here, so you can see this this M ready is given by the subordinate, and that is always high. Okay, so it's you are holding it high, and then this M valid is given by you, so like your module, and that goes high here, and you start sending data. And so in this clock cycle, you see now you have changed the data because this data has been accepted. You know that now we have changed the data, so you put new data here. So D2 is the new data and keep and everything. But then, like at this point, the subordinate suddenly pulls the ready down, right? So subordinate pulls it down. So now what do you do? So what do you do? Like, I mean, in this clock cycle, in this clock edge, you know that some ready is down. So which means you can't change the data. Okay, you should not change the data, like from the protocol that we saw here, right? So you hold the data as it is, right? So then subordinate takes one more clock cycle, and then the next clock cycle, it basically pushes the ready high. So now the subordinate is ready here. So in this clock edge, you know that over here, the data has been accepted. Okay. So you have valid and ready. So this is a handshake. So the data is accepted. So in this clock cycle, you know that you can change the data and you put the new data. And after you put the new data, now you are done. You have nothing to send. So if you have nothing to send, you pull your valid down, right? Okay. And similarly, you have your last over here. So there is how the subordinate knows that how many bytes you are sending, right? So this is the like, I mean, you have last and you are done. Okay. So this is pretty useful. Like, I mean, so we can use, I have used this to do accumulation. So basically you keep accumulating, and like when last comes, you know, there is the end of stuff. So then you can stop accumulate, clear the accumulator and get a new data, right? So otherwise you have to keep a counter, right? So this way you don't need a counter. So that is like a pretty useful stuff. Okay, right. Let's see questions. Why is the 0, 0 in the first two place of D? Is the bit in the different order? Oh yeah. So basically you can see it's a Verilog convention, right? So in system Verilog or Verilog, you like usually do it in this order, little endian, right? So you have 0 on this side and 3 is on this side. So similarly, yeah, you have like the 0th byte and the first byte are high, and the second and third bytes are low. When not M ready, M valid can't even toggle from low to high. Oh, it can actually. So when M ready is low, the valid can go from low to high. That is possible. So that is because you are not sending any data, right? So yeah. So I think yeah, it has to be, that condition has to be addressed. But in the spec, they mention that clearly. So if M ready is down, you can change. You can bring M valid up. Okay. And yeah, according to, I mean, like yeah. So one, like, I mean, some pedantic stuff is like, according to the spec, you should not be waiting for ready. So which means even if the ready is down, if you have data to send, you immediately push the valid up. So you are supposed to do that. Okay. Questions? Right. So let's move on to the next one. Yeah, you can keep asking questions anytime. I'll come back and okay. Isn't there a limit to the burst length? No, there's no limit to the burst length. So you can have, I think you can have as much as you want. In Axie, there's a limit to the burst, full Axie, but in Axie stream, you can do whatever you want. Okay. And the TLAS is sort of optional. Like, I mean, if you are doing some your own designs and if you don't need TLAS, then between your designs, you don't need to put that. Okay. So what is the difference between MT keep and M data? So M data is your actual data. So your M data is like your 32 bits, whatever data you are sending. So D0 is like a 32-bit number, and D1 is a 32-bit number, D2 is a 32-bit number, whatever the actual payload that you are sending and actual processing. Everything else is like just to help you to sort of like, I mean, coordinate stuff, right? And T keep tells you which of these, I mean, in your data might be, so it's a 32-bit number, but it can be like, I mean, I don't know, 10101111 like that. Okay. So something like that. And this T keep tells you which of these are valid. So now here it's 1101. So which means probably this one, this byte, and maybe this byte are valid. Okay, these are valid. And whatever you have here will be a garbage. And don't look at that. That's what you're saying. Okay. All right. Any other questions? So let's move on. So this is a simpler XC stream design. Okay, so basically, if you are trying to build like an XC stream design from scratch, then you can probably follow this. So, but then I think like you probably don't need that. So like I will like sort of gloss over it, and in the end, if you have time, I will come back and uh like go through this carefully, right? So the idea is sort of like, I mean, if you're doing like, I mean, parallel to serial conversion. So you have a parallel bus, 8 bits or whatever, and in this side you have a serial bus, which is 1 bit. Okay. So, and in this side you have a ready valid, and this side you have a ready valid. So what you do is you basically copy the data into a shift register, and then you shift. So you see like, okay, look at this serial, like this S serial value, right? So when you copy, this becomes high, and then you keep shifting, it says high, and then you are done, it's gone. Okay, so and then once you are done, like now your ready goes high. That way you can get new data, right? So at the beginning, basically your ready stays high, and that's how the data comes in. As soon as you get the data, your ready goes down, right? So because you can't get more data, right? So your ready goes down, and then as you are sending this stuff out, the ready stays down. Okay, it doesn't go high. And once you finish sending everything, the ready goes high again. Okay, so that is how, if you are building a module from scratch, you have to build it like that. Okay, so and it is not very hard. Like you can basically build it with the state machine. Okay, so I'll come back. I mean, if you have time at the end, we'll come back and do it like on next week or something. Okay, but so it's like a system developed code for how to build this state machine, and sort of like well done ready stuff. Okay, yeah, and this like a simulation of these things. All right. So now let's look at how do you convert like your normal designs into XStream. So that is what's sort of more important. So I'll talk about that. So like this is our vector multiply add we saw in the beginning. So pretty straightforward. And yeah, pretty straightforward. And now the question is like now this vector map, it basically it can do stuff every clock cycle, right? So it can do stuff every clock cycle, and as long as and it has an enable pin, right? Like so you can enable and disable. So when enable is down, it won't do anything else. It will just freeze. Okay. And when enable is high, it will just do stuff, right? So this like a simple straightforward design, and this is something that you can always write. And if you are writing a neural network accelerator or something, you can write like this, right? So and now what if you have a module like this, then how do you convert this into access stream, right? So to convert this to access stream, this is what you do. So yeah, so like I think this should come first, but okay. Um, right. So now, right. So, okay. So basically, if you are converting that that simple module, that is this one, right? This is your simple module. And now you want to convert this simple module to a full axis stream module, like this, right? This is your axis stream module. So to do that, you need to handle this valid and ready stuff, right? So how do you do that? So you have, I mean, you will get an input like this data. That is the one that you actually processing, and then you will have this thing is valid, and like you have S ready going out, and M data, M valid, and M ready coming in, right? So these are the ports, and how do you connect these ports? So the key thing over here is basically now the key problem is like the stall. Okay. So what is the stall condition? So the stall condition is this one. That is, this is the stall condition, right? So stall means M valid and not M ready, right? So that makes sense, right? So when your M valid is high and M ready is not high, okay, M ready is low, That means now you have a problem. You can't push data. You have to hold everything steady without changing anything, right? So now during this stall condition, now basically you have to stop everything. You have to freeze everything and all that. Also, you have to tell whoever is your manager. Okay, so your manager is somewhere on this side. Okay, and your subordinate is somewhere on this side, right? Like you are sending data to the subordinate, you are getting data from your manager, right? So if your subordinate says that like they are not ready, right? So now you have to stop everything and you have to tell your manager that like you also not ready, right? That is why it's called the back pressure, right? So we have to basically tell like, I mean, it goes back, right? From the subordinate to all the managers. So you have to, how do you do this? So, and you freeze the module and you have to tell them. So this is how you do this. So what you do is basically you have this enable pin, okay? So you set this enable pin as invalid and not template. So I think that is yeah. So yeah, basically you have to use this as your the the enable pin, right? And valid basically goes like this. So yeah, okay. So I see. Okay. So the idea is like, I mean, so this is a stall condition, right? So this is a stall condition, stall. So what you are doing is the enable signal you are giving to your vector multiplier adder is basically not stall. Okay. So whenever it's not stalled, then you keep working. So whenever it's a stall, then basically you freeze this whole module. Okay. So nothing happens. You freeze the whole module. And then that also you give it as your S ready, right? So whenever you have a stall condition, your S ready will be down. So that way your manager will not send you any data. Okay, you're also frozen. You will tell the manager to freeze as well, right? And similarly, yeah. So and then what do you do with S valid here? So the S valid, you have to delay it by the same number of clock cycles as your module vector multiplier. Okay. So basically you have to synchronize so the data comes in and the data goes out. So the valid should go out with the data, right? So if it is a simple module like this vector multiplier, you can just put a delay. And if you know the certain number of clock cycles is fixed or something, you can just put that many delays and you can do that, right? So otherwise you have to, I mean, as you prepare the data, you have to prepare the valid also. Okay. So that is not hard. Okay. So by doing this, we can basically convert any of these simple modules into access stream. Okay. So by handling this ready and valid correctly. Okay. All right. So do you have any questions on this like ready, valid, and how to make stuff access stream? This valid delay should be also dependent on the is ready as well. Is this right? Because we can't start delaying the valid unless, yeah, okay, that is a good point actually. So I think I should put the arrow here. So because that this is valid, no, it's not. Because the S valid will be held constant. So you don't really have to worry about that, right? Because, hmm, no, but then if there are bubbles in there, okay. So I think, yeah, I think you should what actually do this. So the delay also should have an enable signal. Okay. Yeah. So that is it's done here. It's not done in the diagram. Okay. Yeah. So basically we should use this as enable for the delay as well. Is that your question? Okay, so if the reset and an enable both are not accepted, then since we haven't specified a condition, it will act as a latch and keep the current state. Oh, not really. So, so that is a sort of a misconception about Verilog. So that is like, I mean, I think like, I mean, so when I was in undergrad also, like, I was told this, but that's not like strictly true. So you don't really have to put a else condition here. Okay. So that is only true for always com. So like if you are writing a combinational module. So if you are writing a combinational module, if you put an if and else if and something, and if you skip the else condition, then it becomes a latch. Why? Because like the behavior that you want is you want it to hold the data. If that is not true, right? So and a combinational module can't hold the data unless it's a latch, right? So then the tool will create a latch for you because that's what you're asking, right? So that is only true for com. But if you are doing like if you are doing this flip flop that is always at passage clock, if you are doing a passage clock, then the behavior of flip flop is to hold data, right? So you don't need to create a latch to hold data, and it doesn't make sense anyway, right? So you can just put else if enable begin. So and then like I mean the tool will just make it like a enable pin. It won't make it a latch. Okay, all right. So there is no latch inference here. Okay. Any other questions? What does it mean by mlast? So in this particular example, the mlast doesn't mean anything. But then because we are going to connect this to a DMA, so the DMA needs an mlast and it has an mlast signal. So that is how the DMA knows that how much data you're copying from the memory, right? So you tell like I want 1024 bytes or something, and at the end of 1024 bytes, the DMA will give a mlast. And then on the other side, you also have to give an mlast at the end of 1024 bytes. So then only the DMA will correctly copy everything, right? So because the DMA needs mlast, we are a last signal, we are actually using that. Okay. So we are like taking the last from here and we are sending the last to the other side. Okay. Should we have a delay? Why? So, I mean, we need a delay here because the vector multiply add has latency, right? So this has like a 1 clock latency here, for example, and the modules that you write later on like will also have latency, right? You'll have multiple blocks to do stuff. So which means they are not combinational, right? Like they have pipelines and everything. So because of that, like I mean, now your S data will not appear on the corresponding M data will not appear at the same time. It will take after some clock cycle. There is a delay, right? So then you have to delay your S valid also similarly, okay, after a certain number of clock cycles. Okay. Any other questions? All right. So yeah, if you don't have questions, then we can move on to the next one. Okay, so this is a skid buffer. Okay, so the reason for the skid buffer is basically it comes from here. So now you can see, now this is a very easy way to convert any modules that have like a fixed delay or not even fixed delay. If you have like anything that you know how the like data goes, then you can actually make it into a access stream module very easily, right? But then you might see this problem. So the problem is that you can see the S ready combinationally depends on M ready. That is a fundamental problem, right? So the data comes like this, and you are doing some combinational stuff, and it basically goes directly like this. So this is a combinational path, right? So now this is okay for like maybe one or two modules. Okay, it's fine. But then if you have like a lot of modules, so like we are decoding layer one, layer two, layer three, or whatever. And now what happens is the M-ready from here becomes combinational here, becomes combinational here, combinational like that. So now this is going to be a problem. That is, you are going to have a long path from the subordinate all the way to the master, like through this, right? So now this is a problem. So how do you solve this? Like in the sense, like, I mean, how do you break this path, right? So, and this will reduce your frequency. This will the maximum, and this actually happened to us in our final year project, right? So the longest path was the ready, right? Because we had like a multiple, say, convolution layer, max pool layer, ReLU layer, and like, yeah, so many of that. And then the longest path was the ready. And back then we didn't know how to break it. So yeah, so the way you break this is also like, I mean, relatively simple. So you need a skid buffer for this, right? So that's what we are going to look at next. Okay, so this is the skid buffer, right? So you have to register the ready signal if it becomes a critical path. Okay, so basically this is the diagram from previous. Okay, so if you want to, you have the M ready and you like you want to break it somewhere here in the middle. So for that you use a skid buffer, right? So let's see how we do that. Okay, so the problem is basically now you can't stop the data flow in the same clock cycle without combination logic. Okay, so that's sort of the fundamental problem, right? So the thing is, you can't just register ready, right? If you only put a register in the ready buffer, what happens? So on the ready line, if you just put a register or something, let's say you put a register here or something, okay? So now what happens is basically, now let's say you keep sending data. Okay, so let's say you keep sending data and you can't send it after like your what okay, so like your subordinate is not ready in this clock cycle, right? Your manager will only know in the next clock cycle because you have a register, right? The register will delay the signal. You will know only after one clock cycle. So which means in the current clock cycle, your subordinate is not ready. Okay, your subordinate is not ready. So which means you can't push your data. You have to hold your data, but your manager doesn't know that, like, I mean, your subordinate is ready or whatever, right? So the manager will push the data now. So which means you have to accept this data now, right now. But you don't have any space within yourself to hold the data. You have to take the data, but you can't keep it, right? So what do you do? So for that, that is why you need a skid buffer. Okay, so it's a buffer. You have to buffer this data, and this data basically skids into this buffer in this condition. Okay, so you basically put this data into this buffer. If this happens, that is your subordinate is not ready, so you can't push data, but your manager is valid and his manager is giving data. So in that condition, what you do is you push your data into a buffer, and that is a skip buffer. And then later on, like, I mean, in the following clock cycles, you basically you send the current data, you take the data from here and send it, and like that's how you do it. Okay. All right. So let's see how we do that. Um, yeah. So this is basically how we do this. So like you can have like a state machine which is empty, partial, and full, right? So and you have three states. So empty means like, I mean, you are not sending anything out. So you have nothing to send. So when you have empty, it means like embedded is zero, right? So and your S ready is also one because you have nothing to send, but you can receive the data, right? So the skip buffer is a module by itself. Oh, it doesn't do anything other than doing this breaking the ready part. Okay, so it doesn't calculate anything or anything. So it's just a buffer, right? It just like breaks the ready signal and it registers the stuff. Okay, so again, it's very modular. You can put it together with your existing modules to get stuff working. Okay, all right. So what you do is basically now, if you're in the empty state, that means you have nothing to send. You say embedded is zero. Your embedded is zero, and your S ready is also controlled by you. And you say S ready is one because you can actually take data. If someone gives you data, you can take it. And now, if it is valid, if somebody gives you the data, right? So now what you do is you move from empty to partial, right? So in the partial state, now you have data because now somebody gave you data, you copied into your register, into the M register. This is a register and this is a register. So you have two buffers inside this. So you copy the data into the M register. So at the same time, you copy, like, I mean, it's valid. So now your M valid is high, right? But then at the same time, you can still take more data, right? You can still continue taking data. So your ready is also, S ready is also high, right? So that's your partial state. So now in this partial state, now you will keep staying in this partial state. So sometimes, like, I mean, if you're like, I mean, if M ready is high, then you will send this data out. And at the same time, if this valid is high, you will take data in. So you will keep on getting data, right? So you'll keep on, so you can stay in this partial state for a long time. Now this happens. Okay, so this is the difficult condition, right? So your difficult condition is that M ready is down. So your subordinate can't accept data, but then your manager keeps giving data, right? So what do you do? So what you do is you can still take the data, but you go into the full state. Okay, so in the next clock cycle, you will become full. So in the next clock cycle, your data, you will copy this data into buffer, right? And at the same time, you will also make your S ready down, right? So that way, like your manager can't send any more data because you have only space for two data within you, right? So one data is like your M buffer, because you are buffering your M as well, and then you are buffering your like this also, right? So you can't have two. You can't actually take for two data, right? Okay. So then you go to your full state, and in your full state, if you get an M ready, okay, whenever you get M ready, then what you do is you come to the partial state. So why? Because like now invalid and M ready. So which means this data is gone. Okay. So now you copy this one into this. Okay. And now you are in a partial state because there's nothing here and you only have data here. That's a partial state, right? And then partial state again, you can keep on going forever. And in the partial state, you also raise your S rate, right? So now your master can send you more data, right? And then if this happens, okay, so that is now you have in ready is high. So you're giving out this data and your master is not giving any more data, right? So if that happens, now you go into the empty state and that way you are waiting for more data, okay? So this is like a very simple state machine of like three states and like, I mean, bunch of the different ways of like in every state, your values are these, okay? So in every state, these are the stuff that you control. Okay, this and this and this are stuff you control, and these are the stuff that is like given to you, right? Like by your manager and your subordinate, right? So based on that, you change the states, and yeah. So do you have any questions in the state machine? Can you repeat it from partial state? Okay, so like when you are in the partial state, so partial state is like sort of you only have data in M. Okay, you don't have in data in D. Okay, so let me put it over here. So in the empty, you don't have any data anywhere. So let me use a different color, maybe uh, green. So in empty, you don't have any data anywhere. So in the partial, you only have data in M, and in the full, you have data in both M and D. Okay, and when you go to over here, then you copy the data from B to M. So you only have data in M, and from here, like you are sending the data out, and you have nothing. And from here, like if someone gives you data, you go into, I mean, you copy the data into M. And from here, if you have basically what if this happens, then you copy the new data into D, right? So that way, like you sort of keep going in this state machine. All right. So yeah, I can describe from the partial form here. So in the like in your partial state, you only have data in M, right? And then if in that state, what happens like if you can't send data, M ready means you can't send the data out, not M ready. You can't send the data out. Yes, valid means like the manager is giving you data right now, right? So which means you have to accept the data because your S ready is registered, right? You can't tell you can't accept data. You cannot say that, right? Because it's registered. So what you do is you take the data still, but you put the data into B. Okay. So you put the data into B, and that way, like you move into the full state. Okay. So when you move into the full state, now you have still data in M because you can't send the data out, and you have this new data which you got from the manager that's in D, right? So yeah, so you are in this state, full state, and you will in the full state, you also keep your S ready down, right? So your S ready is down, so your manager can't send you more data, right? So yeah, so that way, like now the manager will also freeze. So now you are there, you are waiting for M ready to come, right? So if M ready happens, when M ready happens, what you do is basically you can send out this M data. This data you can send it out, right? So once you send out the data, at the same time you have to copy this B into M, right? So now you have data in M again. So now you are back in the partial state. You have nothing in B, right? So you're back in the partial state. And in the partial state, like you will basically what I mean, you will keep this very high also. So people can send you data as well, right? And then from there, like I mean, if this happens, that is if your master is not giving data and if your subordinate is taking your data, then you will go back to empty. Okay. Any questions? Something you don't understand? All right. So once again, the skid buffer is only like it's useful to break this combinational paths in axis frames. So and this is also used in like for axis as well. So like if you and we'll see like I mean like in axis like the way axis is designed, this you can put this skid buffer wherever you want, right, without any problems. So that's very useful. And yeah, is skid buffer part of access stream protocol? No, it is not. The protocol is basically just like I mean how what these things should. So a protocol is basically like I mean how these wires should behave. That is what the protocol says. So the protocol doesn't give you like a Verilog logic of like actually what to do, right? So it only says like okay, this should happen in this these. bus lines should behave this way, right? So skid buffer is a solution to the problem of like now the simple way of like chaining access string modules, which we saw in the previous slide. If you do that, you are going to at some point you will have like a very long path from here to here, right? Critical path, and that will reduce your frequency. So which means you have to register that path somewhere so your frequency can be high, right? So but then you can't simply register the ready, right? Because if you register it, you are going to lose data. So the way to register that is basically, you have to have a module like this. That is a skid buffer. So it's like a standard module. It's like not something that you have to write it yourself. It's like a good exercise for you to write yourself. But other than that, you can just take my skid buffer or something and you can put it in your own designs, right? So you basically put this after your design or between your designs. So that way, like you break this path and then you can have high frequency. Okay. Okay. So okay, so it's 10:30. Let's see, like if we have yeah, I think this one is next protocol. So we'll do that tomorrow. Okay. So yeah, before that, like if you have any questions, you can ask me here. And okay, so like the Verilog part. So right. So this is the state machine that describes this state machine. So that is pretty straightforward mapping, right? So this is called the three procedure style, right? So that is like, you have you calculate the state next like this. Okay. So how do you calculate the next state? So based on the current state, right? So that is like the state next can be partial, full, and everything based on the current signals, right? And then you have like a one always passage where you like write the state next into the state, right? So it's pretty straightforward. And this way you have an access to the state next. So you can use this to calculate, to do all of these stuff, right? So in here, like we are controlling the actual buffer. Okay. So you can see what we do, like we basically the invalid. Okay. So invalid is a register, is ready is a register. So invalid, what we do is if the state ready next is not empty. Okay. So the next state is not empty, then invalid is always high. So like that's the logic. And is ready is like if the state next is not full, this ready is high. So that's pretty straightforward from here. And here, like you see how we put data to the buffer. So if you are in the partial state and your next state is going to be full, okay, if this condition is met, then you write your buffer, your coming data to buffer. Okay, so if you are in this state and your next state is going to be full, then you basically write your data into the buffer. And then how do you control M data? So M data basically comes from S data. So if you are in, if your next state is partial, like you'll be taking from S data. And if your current state is empty, so if you're empty and next one is partial, you get it from here. And if you are in partial, now you just keep getting data from here. Okay, whenever this happens. And if you are in full, okay, you take the data from buffer. Okay, so that is the three about how you control these buffers. Okay, so the next question is what happens when you increase the buffer size? So I think you're asking currently we store only one value here. What if you have more values, right? Like if you have 10 or 15 something, right? So the answer for that is then it becomes a FIFO, right? So you basically first in, first out. So you push data inside and you take out data in the same order, right? So by doing that, it will be and FIFOs are again used to break combination paths as well as to load to help do retiming and stuff like that. So that is a pretty good idea. But then a FIFO's logic will be a little more complicated than this, in the sense like you will have to have two pointers, and then you have to increment and decrement pointers, stuff like that. But then this one is like a pretty simple state machine, right? All right. So yeah, thank you so much. So we can end it here, and if anyone has questions, you can ask me. And yeah, and then that we can see tomorrow.